Today we are going to present our challenge, Great Harmonics Detection System. Our team member are Alejandro, Eduardo, Mateo, Emiliano, and me. So we start with the problem statement. Next page, please. Mhm. So the power grid in Mexico works at 60 hertz, but some electrical devices can make the signal not clean. For example, computer LED lights and motor drivers can create harmonics. Harmonics are extra frequencies in the power signal. They are not good for the system. If there are too many harmonics, the equipment can get hot. It can also damage electronic devices after a long time. So our project is a system that can read the signal, check it, and show the condition in real time. Next, please. Yep. So here we are in the project objectives. Our first goal is to read the voltage signal. So we used the MPT101B sensor. It helps us measure the 120 volts AC signal safely. Then it changes the signal to 0 to 5 volts for the Arduino. Our second goal is to analyze the signal in real time. We use the FFT, fast Fourier transform. It helps us to see the different frequencies inside of the signal. Our third goal is to show alarms. The system uses different states to show if the signals is normal or if there is a problem. So in simple words, our system reads the voltage, check the harmonics, and show the result with alarms. Next. So this slide shows how our system is organized. There are four main parts. First, the sensor part. The ZMPT101B sensor reads the voltage and makes it safer for the circuits. Second, the Arduino part. The Arduino Uno collects the data from the sensor. Third, the computer part. The computer uses processing to analyze the signal. Fourth, the feedback part. The system shows the result on the screen and also uses LEDs. So the process is simple. The sensor reads the voltage, the Arduino sends the data, and the computer checks the signal, and the system shows the result.
Okay, moving to the Wi-Fi, let's delve into our real-time signal processing layers, which implement the fast Fourier transform to ensure accurate diagnostic or processing. People follows three major mathematical steps. First, the DC removal. In this, we have to understand that Arduino follows works in a range of 0 to 5 volts, and this gives us a signal neutral sign of 2.5 volts DC offset that we have to remove to don't get noise in our signal. Then we have the Hamming window. This is due to the resolution of the taking of the sample that finite blocks of data are going to be cut up. Due to these abrupt cut up of edges, create artificial high frequencies that can be converted in noise. This is called spectrum leaking. The Hamming wave smoothly force the bouncing of our data blocks to zero, which minimize the leakage and keep harmonics readings distinct and sharp. And the third one, the magnitude normalization, because we know that the fast Fourier transform uh, count these variations times the number that we take with the Arduino. That's only give us a number, but the sensors work with voltage. That's why we have to normalize it to convert it to voltages. And finally, the performance is optimized peopling, allow our system to track up to 7 harmonics, which is 420 hertz, while maintaining an incredible precision frequency resolution running 1.95 hertz. In the following slide, we can see that is the functioning of the LEDs. The green one being in a safe place. The yellow one when the normalization is up to 0.1 volts, being a be careful zone, and then we have the red critical zone when the value of the normalization is upper to 0.3. The white LED is only turned on when the connection between the Arduino and the laptop is not found in 3 seconds. And the green identifies specific harmonic causing the violation in real time. Then we have the specifications of the box. For this, we follow the specific limits being 150 times 150 times 100 millimeters. For this, we perform an analysis in Fusion for the compression, looking for 100 kilograms being stable. And for the printing, we use a Bamboo Lab P1. For this, we optimize the PLC use using 4 walls loops in each part of the faces and reducing the infill to a 15%.
In the code section, the total code was divided into two files, the sensor and the recollection phase, the combination of which leads to proper data gathering and analysis, allowing for readable results. In the hardware acquisition module, which is the first sensor code, we can see the flowchart of the function. We can see that the code serves as the hardware level data acquisition and physical interface module of the project. It operates at a frequency of 1000 hertz in order to read correctly and make an accurate analysis of the 60 hertz electrical signal at 1 millisecond intervals. It is not done by Arduino delays, but instead it is managed by microcontroller timing so that it can continuously monitor a voltage sensor connected to the analog input pin. The digital values obtained from the analog to digital converter of the Arduino are immediately streamed to the connected computer over a serial interface for real-time processing. Beyond data collection, the Arduino functions as a responsive peripheral indicator display. It constantly listens for incoming single character status updates, and upon receiving a command, an internal state machine manages a set of 4 physical LEDs, which are from states 1 to 4 for the no network, normal status, alarm 1 or alarm 2, in order to visualize it clearly within the box. And it also includes a built-in 3-second timeout protection routine that automatically flips the hardware back to a no network standby mode if the computer communication is lost.
Finally, the last part of the code is the processing of the data. That here is performed the fast Fourier transform using the minim library in processing. Then it evaluates the harmonic by setting the parameters of the Air max, which is going to be the second state, red, and the alarm 1 max to be the yellow state. Here in the flowchart, we can see how it enables the communication with the Arduino. Then in the main loop, we recollect the data and we start processing to different sample rates. Then we compute the fast Fourier transform using the library. We normalize the magnitude metrics into voltage amplitudes for their rate analysis. For each target, we did a harmonic. We extract the voltage. We analyze the magnitude with the warning limits. And if one of those limits are fulfilled, then the state of the LED changes and the system repeats itself. Here we can see as results of a time lapse where the system was connected during high demanding electrical power in the building. So we can see how it changes to their second state of alarm, which we in the yellow LED. And here is the human interface that displays the raw voltage and the harmonics in real time.
For our conclusions, the system successfully integrated. We were able to isolate a high voltage sensing layer at 1000 hertz precision, being able to have real-time frequency domain processing and multi-state visual dashboard. The algorithm and control validation using fast Fourier transform pipeline correctly identified the anomalies, while the event-driven control loop minimized communication overheard by only transmitting state changes to the hardware LEDs, reducing any noise or difficulties through the code. In terms of mechanical and electrical durability, the physical print of the box was successful in meeting our standards defined by our simulations, being able to survive a standard 100 kilogram compressive limit placed on top of it without any structural fractures. As for our areas of improvement and the future scope, we seek to upgrade the interface to allow live interactive modifications of the R max threshold from the slider, as requested in the challenge brief, and to narrow the alarm filtering matrix to selectively prioritize triplet multiples of 3 to strictly comply with localized grid criteria.
That will be all the presentation. We will put a video of the bugs working in real time.